Morning, everyone. So last time we talked about ADMM, and these three steps are the ADMM iterates. So we have three iterates, X and Z. They are the primal updates, and Y is the do variable. So the last step is basically to update the Y. And recall that we want to show ADMM as an instance of the exact proximal point. So we need to maintain three pairs, sk plus 1 and two pairs, sk plus 1 and s to the k, sorry, just one pair. Each one has three elements. So sk plus 1 is xk plus 1, zk plus 1, and yk plus 1. And we also have the ones with tilde. Just like what we show in the exact proximal point framework, we usually show some vk belongs to the epsilon enlargement of t at a certain point x to the k. And now we just generalize this x to the k to be some sk plus sk tilde. And this is a pair including both primal and dual variables. And this v, in our case, is this ratio. It's this the difference between two gradients of w at sk and sk plus 1 divided by lambda k plus 1. Previously, what we had is something like xk minus xk plus 1 divided by lambda k plus 1. So if we use the Euclidean distance, use L2 norm to replace w, then this sk becomes the gradient w of sk is the same as sk. So if you use Euclidean distance, this goes back to the normal setting. And if you also replace the sk by the xk, but now we just generalize it to include both primal and dual information. Okay, so this is a generalization of the inclusion in the IPP framework. So we also need to verify the inequality in the IPP framework. And in this case, it's more general. We are using Bregman divergence because here W is distance generating function. And here we already replaced the gradient of L2 norm square by the gradient of W, the distance generating function. So we are also going to replace the Bregman, the L2 norm square, the normal Euclidean distance by the Bregman divergence using W. So this definition is the same as the Bregman divergence that we have seen in the lecture about mirror descent. Bregman divergence for the function, this distance generating function W between 2 points S and S prime is defined as the difference between the function W at a certain point S prime minus the linearization at S evaluated as S prime. Okay, so this is the same definition for Bregman divergence. And this is the inequality that we need to verify in the IPP framework. This also generalizes the one we have seen before. Right, the one we had previously was like this. Because we are now interested in the smooth case, so we just set this delta k to be 0. This is to handle the non-smooth case. And now let's divide everything by 2. Okay. So this Bregman divergence is a generalization of the L2 distance divided by 1/2, divided by 2, right? So this generalizes this distance. This Brakman divergence also generalizes this distance, and lambda times epsilon, they are the same. Okay, so this is a generalization of the inequality we have seen before. Now let's check if this is true in our setup for ADMM. So let's compute the left-hand side. The first step is just by definition. Because W is defined to be the sum of two L2 norm square, right? And if you compute and here we are just computing the Brakman divergence of each of them individually and then sum them up. Because the Brakman divergence of L2 norm square, so if you replace this by L2 norm square and do the computation, this is going to be just the distance between S and S prime in terms of L2 norm, right? And we also have 1/2. So that's why we can directly use a distance between the 2 points. And because this is, W is the sum of 2 norms. So here the Brakman divergence is also the sum of 2 L2 norm square. Okay, and because when we do we actually set xk plus 1 to be x tilde k plus 1 to be xk plus 1 and zk plus 1 tilde to be zk plus 1. This is how we set these two primal variables. And for the do, it's different. Yk plus 1 tilde right, because zk plus 1 and zk tilde plus 1, they are the same. So this term goes away. We only need to care about the last term. And moreover, we also have yk plus 1 okay, so here is just a difference between yk plus 1 and yk plus 1 tilde. So most of them will be cancelled out. The difference is just rho times zk plus 1 minus zk. Right? So we can simplify this term in terms of z. This becomes rho over 2 zk plus 1 minus zk. Okay, and now
Why does that term vanishes?
they are the same.
Oh, there is.
Now let's compute the right-hand side. So again, by definition and by the structure of this W and the Brakman divergence definition, we still have this the Brakman divergence of W in this form. Okay. Because again, this z tilde k plus 1 is the same as zk plus 1, so we replace this one by zk plus 1. And here, when we show this inclusion, we actually assigned the value for epsilon and lambda. So last time we set lambda k plus 1 to be 1, and epsilon k plus 1 to be 0. So we actually don't have this term. This is also 0. We just need to check whether this Bergman divergence is less than to this Bergman divergence scaled by sigma. Sigma is something between 0 and 1. And from here we can see if we set sigma to be 1, right? These two terms are the same. And after multiplied by sigma, right? Because sigma is 1, so it's also the same. So then the right-hand side is greater enough to the left-hand side because we have an additional term. Okay, so inequality is also checked, and we have given the definition for this mapping T last time, and you can check these three steps actually implies this inclusion. So we have checked both the inclusion and the inequality, and hence ADMM belongs to this framework, right? IPP framework. So we can use the general convergence guarantee, either the pointwise or the algorithmic convergence for IPP framework to show the convergence of ADMM. Okay, so but we will not go through the details again. You can check the general convergence guarantee. And now I'm going to show you a few instances using ADMM to solve constraint optimization problems. So the first example is least absolute deviations.
Professor,
Yes.
before moving on, I just want to make sure I understand why we're using Bregman divergence. So it's more general in the sense that because we're acting over 3 iterates,
Yes.
that's why we can't use L2?
Right.
Okay.
Because we have both prime and do information.
Okay.
We want to combine everything into just one descent generating function. Yeah. But previously, when you just have primal information, you can just use the first part. So it's just L2 norm.
I want to make sure I understood that.
Sure. So let's consider solving this minimization problem. Given matrix A from Rn to Rn, B is a vector in Rn. We want to find a vector x in Rn so that this L1 norm is minimized. So let's try to formulate this problem into 2 blocks using 2 variables A and B. Just put it in the form of ADMM. Recall that in ADMM, the problem we want to solve is, for example, the one we mentioned last time was f1 of x we just want to reformulate that problem into this form where you have 2 objective functions, each for a different variable x and z, and you have a constraint on x and z to connecting the two. And then we can use ADMM to do alternating minimization for x and z. So now let's reformulate this problem into that form. So the reformulation is quite similar to that one. So we have f1 of x plus f2 of z right? We just set the function for x to be always be 0, and fz is just the L1 norm, and we also set ax minus b to be the same as z, right? So the two problems are equivalent. And now let's formulate the augmented Lagrangian. Okay, so we first dualize the constraint and then penalize the constraint. This is augmented Lagrangian. And then we can formulate the subproblems for x and z. So we are given a triple k, zk, yk, right? And then by fixing zk and yk, we minimize the augmented Lagrangian to find the xk plus 1. To be exact, this belongs to a set argmin, right? But here we just simply use equal to some little argmin just to choose one of them. So if z and y are fixed, this term goes away. And in terms of x, this is just a quadratic function. Right? So for quadratic function, we can solve for closed form solution. And here we also assume that A is full column rank. So we assume the rank of A is and the same as number of columns, so that A transpose A, this is an n by n matrix, and this is invertible. Hence, we can solve the quadratic equation. Then we get the solution of A. Right? You can check xk plus 1 is exactly this solution, because this is a solution to the quadratic function. And for zk plus 1, CK plus 1 is, let's do it slowly. CK plus 1 is also an argument of the augmented Lagrangian. But we need to use the latest information for x. Let's use xk plus 1. Because the dual variable hasn't been updated, so this is still yk. And then we need to do the dual variable update. So this is just the basic dual ascent step. What's need to be put here is the gradient of the augmented Lagrangian with respect to y. So taking the gradient, this is only term involving y. The gradient of y is just the ax minus c minus b. And here x is the xk plus 1, z is zk plus 1. Right, so that's the gradient. We just do a gradient ascent step. Now let's do a reformulation to simplify the updates, the three updates. So let's now set yk bar to be yk divided by rho. Then this becomes yk bar, right? for x, we just call this y divided by 1 over divided by rho as y bar. So this is the update for xk plus 1. We are using yk bar. And for zk, we first change this yk to be rho yk bar z. Right, and then we can try to complete the square. Just try to push this term, this minus sign, into the quadratic. Then it becomes this quadratic, right? Ignoring other constant terms because they do not play a role in this argument. And noting that this is actually a quadratic function in terms of z plus L1 norm in z. And this is actually a proximate mapping for L1 norm. Right? Proximate mapping for L1 norm is what we call self-thresholding. So element-wise, it's defined as this. Here, this y is a scalar, but you just apply, so this is a vector, just apply this operator onto each of the elements. Okay, so this is, the z update is just a self-thresholding because this is a proximate mapping for L1 norm. And for the dual-variable update, we just divide the whole equation by rho. Then this becomes yk plus 1 bar, yk bar, right? So this is the final 3 updates. 2 primal, 1 do, and we just use the scaled information for dual variable. Okay, so this step is explicit, and you can also operate the self-thresholding. This step is also explicit. So this is a way to reformulate this primal problem into a primal do problem by adding a constraint. So this is more or less like adding a dummy variable z, right? And then you can do this alternating minimization.
Excuse me.
Yes.
All is clear. I just have a question about that's minus rho yk bar, the term that we wanted to include it into that.
You can expand the square here, and then they are the same.
Yeah.
Right? Just ignore all the other constants.
Yeah.
And now let's do another example. Right, this is the formulation for lasso. You want to find a sparse solution to the regression problem. So we also want to formulate it as minimization of two functions, right? f1 of x plus f2 of z, and then you have a inequality constraint on x and z. Then we can use ADMM. So let's reformulate it as minimization over x and z. Right. So we simply take the first term to be f1 of x, call the second one as f2 of z, and then obviously the constraint we need to have is x minus z is just 0, right? So the two problems are equivalent. Again, let's write down the augmented Lagrangian. Okay, this is the augmented Lagrangian. And then let's do the 3 updates. So for x, it's quite similar to what we had before, because in terms of x, this is again a quadratic function. So we will have an exact solution. And for the z update, we still minimize this augmented Lagrangian. And so this is the argmin formulation for z. And for y, we also just do the dual ascent. So the gradient for y is xk plus 1 minus zk plus 1. And we can also do the reformulation by scaling the yk. Okay, so by rescaling, this is our xk plus 1. And for the zk plus 1, we can also try to complete the square using the subtracting operator. We have this update for zk plus 1, noting that here we have a tau, because this is, right, you divide everything by tau, by rho. This is approximate mapping for tau over rho L1 norm. So you need to have this tau over rho. And for the y update, the scale of the y update, this is a simplified form. Okay, so this is a way to solve lasso using ADMM. Okay.
Excuse me. Oh, sorry, excuse me. Does this algorithm work better on, for example, this problem other than previous algorithm that we studied?
For some of them, it's better to. So yeah, for lasso, you can also directly use you can directly solve this problem using, for example, self-thresholding. just use approximate mapping. Yeah, this is just a way to reformulate it. I don't know whether this will be better in practice, but for many other problems, when you have more than two components, for example, in distributed optimization, suppose you have, so this is a typical problem that you want to solve in distributed optimization. You have a communicating network, right? These are your agents, and you have the network may be something look like this. It's not a complete graph. Only the neighbors with only the neighbors with an edge can communicate. But if you want to communicate between the two agents, you have to do a detour either like this way or go this way. So while you still want to keep your data private, so for example, you are a user that only using this agent, so you only want to store your information, your personal data in this agent. You do not want the agent to share the information to others. Only some data that are not private, you want to communicate with others to do the global computation. So the optimization problem sometimes like minimization, summation I from 1 to M is the number of agents, number of nodes in the network. Right, this is the optimization problem you want to solve. This Fi is the local objective function in each agent. This function Fi incorporates some data, some private data only in this agent, right? But so in the end, the goal is to use all the computing resources to collaboratively solve this minimization problem. It's kind of like a consensus among all the agents. We want to find an X that is shared in all the nodes, right? We want to make a decision in the end. But so one of the ways to solve this one is as you reformulate the problem by introducing m copies of xi. So you want to solve this problem. Xi is some local information in each agent, but in the end, you still want them to be the same. So you will have many constraints. Right, this is the problem you want to solve. And in this case, ADMM is much better than others because, first of all, you can do local computation, right? And then you do communication. Local computation is like the way we solve block by block, X and then Z. We do alternating minimization. So this is a better structure for ADMM to be practical.
Thank you for this good example.
And now let's see a more complicated example. Now let's consider this problem with separable structure. So this is just like the example I just gave. You have f5 xi where you have this constraint. So this is just one constraint, not like what we mentioned before. You have x1 equals to x2 up to xm. That is multiple constraint, but this is just one constraint connecting all the variables. And here we assume the function fi's are convex and the sets xi's are closed and convex. So if you want to apply ADMM, the first out may be something like this. So we still formulate augmented Lagrangian. Right? So we just introduce one variable y for this single constraint, and then we dualize and then penalize the constraint. This is the augmented Lagrangian. And then the ADMM we are going to have simply by alternating minimization for the m prime blocks, and then do the dual set for the y block. So the algorithm will be something like this. Right, we just do this coordinate or blockwise update. This is like something like Gibbs sampling, right? You just fix all the previously updated blocks and also keep all the unchanged blocks. And then, so we just change the ice block, but all these blocks before it is with k+1 iterate. All the blocks after it are the case update. And this y is actually yk. Right, then we solve this minimization of the augmented Lagrangian to get the ice update. For y, we just, after you do all the primal updates, all the m blocks, then for every xi, we use the k+1's update, then do this dual set step. This seems to be a natural way, but the difficulty is that we do not have convergence guarantee. For ADMM, the example we just gave was for 2 blocks, right? That is for m with 2. For this, we have convergence guarantee. You can just follow the IPP framework, right, to show either the pointwise or the ergodic convergence. So for m equals 2, we have convergence guarantee. for m equals 1, if it's just one block, then the method, then the ADMM becomes augmented Lagrangian method, or what we call MOM, method of multipliers. So for augmented Lagrangian, this is just like because we showed that augmented Lagrangian is proximal point method applied to the do problem. So this is an exact version of the proximal point method. You also have convergence. This is exact, this is exact. For both of them, we have convergence guarantee. Well, for m greater than or equal to 3, when you have more than 2 blocks, then in general, we do not have convergence. You can actually construct some counterexamples to show divergence. Right, so this is the issue. You can still do minimization like this, but the problem is that you do not have any convergence guarantee. Right, so we cannot naively just introduce one durable and solve that problem using alternating minimization and introduce that simple augmented Lagrangian. We need to do some other reformulation to make the problem to be 2 blocks. Right, multiple blocks are not suitable here.
In there, for every iteration, we have to do when m is 2, we have to do 2 minimization. Am I correct?
Yes. Like x and z.
Yeah. Putting xi equals to constant and do minimization over other.
No, xi is not constant. You are minimizing over xi.
Yeah. Excuse me. Putting other variables constant and doing the minimization over xi and otherwise, and doing it iteratively over and over.
Yes. Yeah. So first do minimization for x1, and then you get x1 k plus 1. Now you minimize over x2. But from x3 to xm, they are the case update. You do not have the k plus 1 update information. So we need to make the problem to be 2 blocks. The way we do that is by introducing m dummy variables zi's. So we set each ai xi to be zi, and we let the summation of zi to be b. So this is like m constraints, and this is a single constraint. We do not change the objective function. So this is for xi, zi, this is minimization. And now the 2 variables, 2 blocks, we have 2 huge blocks. For x, we concatenate all m blocks together. So this x will be a really long vector. And this z is also a long vector. So now the constraint for x is the Cartesian product of all the sets x1 to xn. And for the z, the constraint is this. The constraint set is this one. It's just a linear constraint, summation zi equals b. So this is like a block-wide summation. And now let's write down the augmented Lagrangian for this problem. So because here we have m constraints for each of them, we need to introduce a new variable that is yi. Here we just dualize and penalize this constraint. We do not touch this linear constraint summation zi equals b. We only dualize this one, so we only introduce durable to this constraint, but not the second one. We will keep the second one in the minimization. So this is the augmented Lagrangian for the two-block optimization problem. And now let's do the ADMM updates. For X, we do it block-wise. This is for every block I. So there are m iterates, right, for each of them. And for every one, for the Ith block, because other blocks do not play a role in this minimization, so we just focus on the one associated with index I, right? Just Ith block. Others just go away. And here, this is the. So we basically just copy down what's for the Ith block, but for the Y and Z block, we just use the case update. So this is the X update, but you need to do it for m copies. And for Z, we just have one update. This is because we still have this constraint for all the Z. So this Z is not separable, right? X is separable, Y is separable, but Z is just one whole, just a huge block because we have this constraint. So since we do not dualize this constraint, it's not unconstrained. We still have this one. So in the argmeans, we need to have this one, and the objective function is still the summation of m blocks. But for the X block, you can use the k+1's update. For Y, it's still separable, so you can still do the block-wise update. It's only the X is a huge block. So we need to do more reformulation for the Z update to make it easy to solve. So let's introduce, because we have a constraint here, so let's introduce another Lagrange multiplier associated with this constraint. So let's introduce the multiplier lambda. Lambda k+1 for the k+1's update. Then let's write down the Lagrangian for the Z subproblem. Right, we just dualize this constraint using the multiplier lambda k+1. This is the Lagrangian for this minimization problem. So to solve this problem, let's take the gradient with respect to each of the Zi. We just set gradient of with respect to Zi to be 0. Then let's solve for Zi k+1. So then we have Zi k+1 is equal to AI xi k+1 and this is the Ith block for Z. Now let's reformulate this equality to see what lambda k plus 1 is. Note that this lambda k plus 1 is the same lambda k plus 1 for every I here, right? This is for every I, and this is also for every I. Let's compare this lambda k plus 1 formulation with yi k plus 1, right? They are exactly the same update. So we observe that lambda k plus 1 is equal to yi k plus 1 for any I. Now let's go back to this X update. Let's see how to reformulate the X update using the knowledge of this lambda. Because this holds for any k, so we also have lambda k. So for the previous iterate, this is yik for any I. So our X update can be reformulated as and also we can, because of this, we can do the blockwise update for Z. Previously, Z is a huge block to us, but now we can do the blockwise update. So for Zi k plus 1. And also we can replace the yik by lambda k. Replace the, this is it's already in the form of lambda. So let's use lambda to update Z. From here, let's recall that we have a constraint that summation of Zi for any iterate, no matter what k here it is, the summation has to be b. So let's check what this constraint can give us, because we haven't used that constraint. Here we just relax the constraint, but in the end you still need to use this constraint. Okay, so let's do the summation of Zi. So on the one hand, it is equal to b. On the other hand, let's try to do this summation. So this implies lambda k plus 1 is equal to lambda k because here we have m copies, the same quantity, so you can factor out. So you can take this outside of the summation and then divide the whole thing by m. You get the update on lambda k plus 1. So lambda k plus 1 in terms of lambda k and the latest information for xi for the k plus 1 iterate, you have this update. So now we get rid of the individual two variables yi, right, for each block, but we have this this two variable associated with this huge block, this single inequality, right? So in the end, the way we solve the problem is given xk, zk, lambda k, you update it to xk plus 1, zk plus 1, and lambda k plus 1. Lambda xk plus 1 and zk plus 1 can be done blockwisely. And for lambda k, you just do this one block update because lambda k plus 1 is the same as yk plus 1 for any individual block. So in the end, you just do this update, and this lambda update. So this is a way to reformulate the problem of separate structure into a two-block optimization problem. And then you can still use ADMM to solve for it, and you still have convergence guarantee because this is for two blocks, right? So this is a like non-trivial reformulation of ADMM, different from the lasso and the deviation problem we just saw. Okay, so this finishes the lecture on ADMM. Next time we will be talking about Nansdorf smoothing. So it's a way to solve non-smooth optimization using smooth techniques, but we first need to smoothify the problem. And we can see an improvement compared with the subgradient method.
Excuse me. Within here, using that Z highlight, we have reformulated n greater than 2 to n plus problem.
Yes.
So we have done to resolve this problem.
That's fine. That's fine. I didn't know if someone had slept. No problem.
I have one.
Yeah, there's pictures of it on our Instagram. Like we're lucky.
错了，我加个微信。
它这个是条件吗？
Oh, sorry.
另外，
要正的。
要正。
哦，行，
Oh, it's honestly crazy that they were. I know, like they were so competitive. Like it was hilarious. I don't know. Like they were really into it. Yeah. But we could never, we don't have any meetings, so it's bad. Oh, really? Yeah, because we have to giveaway? Yes. What? Sure. I don't have any. I would love to. I can't pull up.
That's it.